So now that I've introduced the concepts of linear independence and dependence, as well as the concept of span, from these two concepts results another very important idea in linear algebra that is known as a basis. So let me give you a definition. So definition. Okay. So let W be a subspace of V, where obviously W and V are sets, and let B be a subset. B be a subset of V. Then B is a basis of W if the following two conditions are met. So first of all, span of B needs to equal W. In other words, B generates all the vectors in W, or just B generates W. Second of all, B must be linearly independent. So if these two conditions are met, then we have what we call a basis. Okay, so let me give you some examples. So example number 1. So 1 is the set B equal 1, 0, a basis of R2. Okay, so remember what we need to check for a basis. We need to check that span B equals W and B is linearly independent. Okay, so let's start with span. So does span B equal W? Or in this case, does span B equal R2? Okay. Well, for span B to equal R2, that means that B must be able to generate B. So that means that B must be able to generate any. So that's the important part, is any vector in R2. And remember what the vector space R2 looks like. It looks something like R2 is equal to the vector AB, so with a component A and a component B, such that A and B are real numbers, so belong to the real numbers. Okay, so B must be able to generate any vector. So that's the important part, to generate any vector in R2. Well, if we take an example, like 0, 3, and we say, is 0, 3 equal to C1, 1, 0? So we want to solve for C1, right? Well, we get a system of linear equations. We get 0 is equal to C1, and then we get 3 is equal to 0. Well, obviously this is a contradiction. This is impossible. So as a result, the vector 0, 3 is not generated by B, by the set B. Okay, so that means that span of B does not equal R2. Okay, so automatically, if we have this, if our first condition here fails, then what we can say is that B is not a basis. B is not a basis of R2. So automatically we can conclude that. Okay, so that's the first example I wanted to give you. Now the second example is B equal 1, 0, 0, 1, 1, 1, a basis of R2. Okay, so that's the second example I wanted to give you. So first of all, what do you check? We check if span of B is equal to R2. So we want to know if this is true. Well, remember what I said right over here, that R2 is basically any vector that looks like this, where you have an A component that belongs to the real number and a B component that belongs to the real number. Well, that means that any vector in R2 can be represented by, so we have AB, where A and B belong to real numbers, and we can write AB as A 1 0 plus B 0 1. And it just so happens that 1 0 and 0 1 are two of the vectors that belong to B. So this one belongs to B, and this one belongs to B. Okay, so it doesn't really matter in this case that 1 1 isn't part of this equation. We could just write that 1 1 is like 0 1 1. If we really wanted to show that AB was a linear combination of all the vectors in B, we could just write 0 times 1 1. But this part doesn't really matter. What matters for span is we're trying to check if all the vectors in R2, in other words, vectors that look like this, that look like AB, can be represented by a linear combination of the vectors in B. And in this case, they can, because 1 0 belongs to B and 0 1 belongs to B. So in this case, any vector in R2 can be generated. Generated by B. Okay, so span B is equal to R2. Okay, so that's the first condition. We've actually confirmed that the first condition is true for this set. Now let's check linear independence. So is B linearly independent? Okay, so in other words, I want to see if for C1 1 0 plus C2 0 1 plus C3 1 1 equal 0 0. I want to see for B to be linear independent, C1, C2, and C3 need to be 0. Right? I'm trying to find if this system gives me the trivial solution. So let's write out the system of linear equations. We get C1 plus C3 equals 0, and C2 plus C3 equals 0. Well, what do you notice here? You notice that in this case we have C3 as a free variable. In other words, that means that C1 and C1 can be expressed in terms of C3, and C2 can be expressed in terms of C3. So this means that there are actually infinitely many solutions. And there isn't just the trivial solution. So for example, I can say, let's say, take C3 equal 1. So that means that C1 is minus 1 and C2 is minus 1. Well, that actually does work, because if you have minus 1 here, and 1 here, well, minus 1 plus 1 is 0, and minus 1 plus 1 is 0. So we get solutions. Well, we do get the zero solution. The trivial solution. The trivial solution belongs to the solution space, but we have an infinite number of solutions. So there's not just one solution. There's not just a trivial solution, but there are others. And so by definition, that means that B is not linearly independent. not linearly independent. And in that case, that means that B is not a basis for R2. Okay. Okay, so that was my second example. Now let's go with a third example. So 3 is B equal 1 0 0 1 a basis of R2. Okay, so I want to check if 1 0 0 1 is a basis of R2. Okay, well, what do I do first? I check if span of B is equal to R2. Okay, well, remember from here, any vector in R2 can be represented. Any vector in R2 can be represented as AB. Right. So any vector in R2 can be expressed as AB, where I can actually write AB as A10 plus B01. So in fact, AB, any vector in R2 can be represented as a linear combination of the elements in B, because this thing belongs to B and this thing belongs to B. So if I take any vector in R2, then I can express it as a linear combination of the vectors in B, in my set B. So I just want to give you an example. I know I talked about this before, but just to sort of emphasize it. So if I take, let's say, minus 7, 3, well, I can write that as minus 7, 1, 0, plus 3, 0, 1. And so I've written minus 7, 3 as a linear combination of 1, 0, 0, 1, or in other words, as a linear combination of my set B. Okay. Similarly for anything, right? You can take 10, 11, or 20, 20, 76, or anything, right? Anything. Any vector in R2 can be represented as a linear combination of the vectors in B. Meaning that, so this means that span B equal R2. So span B equal R2. Okay, so that's the first condition. The second condition is B linearly independent? Is B linearly independent? Okay. Well, to check that, we need to create a sort of a system where we get C1 1 0 plus C2 0 1 is equal to 0 0, and we want to check if C1 and C2. So if the solution space is the trivial solution, we want to see if the trivial solution is where we get all zeros. So we want to see if C1 and C2 are both 0. Well, if we write out the system, we'll actually get straight away that C1 is 0 and C2 is 0. So this is the trivial solution. And thus B is linearly independent. Okay, so B is a basis of R2, and in fact the basis B, so the set 1 0 0 1, this has a special name. This is actually called the standard basis of R2. So you'll see a lot more of standard bases in linear algebra, and I'll try to do some more videos on checking if something is a basis or not, and on finding if something is a basis.